Hello everyone, my name is André Pucciarelli and I will talk about thermodynamics and Rankine cycle here in this lecture. Don't know me, I am Brazilian and I make my lectures in Portuguese of course, and lots of students ask me to make this international version of my lectures. So I would like to start with Rankine Cycle because it's one of my greatest videos and most viewed in my channel. So I really apologize about my awful pronunciation and the words, and if any word I pronounce wrongly, please don't mock me, okay? So let's begin the lecture. We'll talk about Rankine cycle, and it is one of the most important cycles in thermodynamics because it's one of the most used in power plants, in nuclear reactors, and most of the applications that we need to generate power we use these Rankine cycles. And the efficiency of this cycle is higher than the other cycles which it's available in the industry, but this one is one of the most important. So let's begin. Of course, I'll always make a warning to enumerate the topics that we are talking in this lecture. Here I will remember the thermodynamics diagrams and the fluid state. So I will talk about the TS diagram, the temperature entropy diagram, and the state, and I will show you how we locate the systems looking to the diagram. So we have the subcooled liquid, liquid plus vapor, and superheated vapor. So I will make a little review. Of course, you should know this to understand this class, and I will talk about a little bit about this in this lecture too. I will talk about the ideal Rankine cycle. So I will not talk about heat losses or pressure drops. So this is a matter for other video or other lecture. Here I'll talk a little bit about the process that occur in the components, about the component itself, and the approximations we should make to make an analysis, an easier analysis for you to understand the cycle and to know how to measure all the heats, all the work and powers that in all the components we have in this cycle. So of course we'll apply the thermal laws on the components for us to understand and know how to calculate the power generated at the turbine, and the heat input that we have in the heater, and the work, the power we need to initiate the pump to operate. So everything we talk, this stuff I told you now, I will show in this lecture too. And of course I will show you how to calculate the efficiencies of this cycle. Is one of the most important things I would say here. And I will resolve two problems here. The links will be in the descriptions of this video. So of course, if you like this class, look at the exercise for you to understand everything I spoke here. So let's begin here. Let's talk about the thermodynamics diagrams. Here we have the two axes, of course, x and y. And here we have the diagram TS, which we have here in the y, in the vertical axis, we have the temperature, and in the horizontal axis we have the entropy. And the diagram, it is like this. It has this mountain of shape. And here we will have the two pressures. We work between two pressures. A higher pressure, I call it here pressure 1, and a lower pressure, I call it here pressure. And of course, as I showed here, the higher pressure we show here up on the diagram, and the lower pressure we have in the bottom of the diagram. So P1, P2. P1 is higher than P2. And here at this diagram, in this black line, we have the saturated line. Here, if I am here in the left of the diagram, I have saturated liquid. And if I am here at the right of the diagram, I have also saturated fluid. But here I have the fluid is completely vaporized, and here I have the liquid is complete liquid. And here in the left of the diagram, we will have the temperature is under the saturated temperature. So if we, for a pressure that I have the saturated temperature, and if the temperature is lower than the saturated temperature, I have subcooled liquids, because the liquid is a temperature above the temperature saturated temperature. Okay, and in the level 2 we have between the inside the diagram, in between the position of vapor, saturated vapor and saturated liquid, we have in all this region we have liquid plus vapor, because I am at the temperature and at the saturated temperature, and here I have vapor plus liquid. And of course, if I have subcooled liquid here at the left, I have liquid plus vapor here in the middle. At the right, we will have superheated vapor. Of course, the temperature of the superheated vapor is higher than the temperature saturated temperature H1 and H2. And if you will talk about the amount of energy of each stage, we will notice that the level 3 or the superheated vapor, it has most energy than the other two levels, liquid plus vapor and subcooled liquid. And we should know here that at the left we have subcooled liquid, at the middle we have liquid plus vapor, and at the right we will have superheated vapor. Okay, so now we made this review about the TS diagram. We will enter here at the ideal Rankine cycles. And here I will talk about the components of the cycle. So first we have the heater. The heater has as the name says, and he has the function to receive heat from another source. We'll burn a fuel, we'll use a solar panel, so the sun will heat the fluid and will put more energy on the cycle, and that is its function. We'll also have a turbine. The turbine is responsible for produce the energy from the cycle, or we will expand, we will increase the specific volume of the fluid, and we will produce power. And of course we have a condenser. The condenser has this function to return the fluid from vapor to liquid. And we have the pump. The pump is responsible for move the cycle. Okay, it increases the pressures at the entrance and the outlet, and we will increase the pressure so the fluid will flow in all the cycle. So here the fluid exits the heater, will enter in the turbine, and after the turbine the fluid will flow to the condenser. After the condenser it will enter the pump, and the pump, as I said, it will increase the pressure of my flow and will throw back the flow at the heater to initiate again the process, the cycle. So here at the turbine, as I said, we will produce power. Here, of course, the axis of the turbine at a generator, and of course we will produce energy, electric energy or rotational energy, as any kind of use we can make to this energy. Here at the heater, as I said, we will burn some energy, we will use some kind of energy to increase the energy of our flow and to produce vapor. Here we will have liquid, here at the entrance of the heater, and here at the outlet of the heater the fluid will be at a vapor state. But after I will detail a little bit more about this. Here at the condenser, the condenser will be responsible to transform the fluid again to liquid. And how we'll make this? We will remove energy from my cycle. So here at the heater, we will put more energy, more heat at the system. And here at the condenser, we will remove this heat that we will have here in this cycle. And here at the pump we will use energy, we will use electric energy to increase the energy of the cycle and will make the flow to exist. Okay, so here now what will I do? I will show here all this process I told you at the components, and will show here here at the TS diagram as I showed you at the first slide. So the first point we'll use here is that at the outlet of the heater and the entrance of the turbine, we will consider that we will have the same fluid state. Okay, if I have vapor, superheated vapor here at the outlet of the heater, at the entrance of the turbine, we will have also superheated vapor. And the same thing we will do about the other components. At the outlet of the turbine, we will have some fluid state. It will be the same at the entrance of the condenser, the same thing to the outlets of the condenser, the entrance of the pump, and all the cycle will be here. And that approximation we can make because we are not considering here the heat losses at the pipes or at any of the components, and we are not considering also the heat drop at the pipes too, and we are also not considering heat losses at the condenser, heat losses at the pump, heat losses. Of course we will have the heat loss here at the condenser and the heat enters here at the heater, but in the pipes we will not have heat losses. It's very important for us because we're talking about an ideal Rankine cycle. Okay, so the first point we analyze is the entrance of the turbine and of course the outlet of the heater. And here at the point 1, as I showed here, we will have superheated vapor. Okay, so the fluid will exit here the heater as a state of superheated vapor. Okay, in some cases we can have saturated vapor here at the outlet of the heater, but the most common configuration here shows that in the outlet of the heater we will have superheated vapor. So here at the turbine we will expand the fluids, or we will remove heat from our flow as power here. And here at the point 2, at the outlet of the turbine and the entrance of the condenser, we will have here liquid plus vapor. And as you can see, as you can see here, the X that I show here, it's the vapor quality of the flow here. And the vapor quality, as you might know, is the relation of the vapor mass of the system divided by the total mass of the system, meaning that higher is the vapor quality, higher is the amount of vapor here at the turbine, at the outlets of the turbine. So here at the point 2, at the entrance of the condenser, we will have liquid plus vapor. As you can see here, at between the points 1 and 2, where this line is completely vertical. And that is because we consider that this process between 1 and 2, we consider that is isoentropic. Because the entropy here at the point 1, it's the same entropy at here at the point 2. And this is because we consider that this process is reversible. Okay, and we won't have here heat losses here also, as we have here at the condenser at the heater. We have heat input here at the heater and heat output here at the condenser. But here at the turbine and at the pump, we'll have just work, power here at the pump and here at the turbine. We won't have energy leaving or entering at the form of heat. Okay, so here at point 2 we have liquid plus vapor, and this process is isoentropic. Okay, here at the condenser, as I told you, we will remove heat from the system, from the flow, and we will have here liquid, saturated liquid. Okay, so here at the condenser, all the vapor here we will have here at the entrance of the condenser will be transformed into liquid. Okay, because so here, as we show here at the left of the diagram, we'll have here the saturated liquid. Okay, and as I told you before, at the pump here we will have the increase of the pressure of the system. As I showed here, we will work at two pressure, a higher pressure P1 and the lower pressure P2. So as I told you, we will have at outlet the condenser, we will have saturated liquid. And here the pump will increase this pressure. And as I told you, we won't have heat leaving or entering here at the pump. So the process 3 to 4 will be also isoentropic. And as I showed here, we will increase the pressure. It will happen isoentropic, so this line will be vertical. And here, as we are at the left of the diagram, we will have subcooled liquid. And of course, this process between 4 and 1, we will begin again the cycle. So the heater will make the fluid from subcooled liquid, it will be again superheated vapor. So I forgot to tell you about something. The pressure inside the condenser and inside the heater, they happen to the pressure here will be constant. So the pressure at the point 4 and point 1 will be the same, and the pressure at point 2 and the point 3 will be the same also. And also we'll have to point out that the process between 1 and 2 and 3 and 4 will be the isoentropic. Okay? And here, okay, I already showed here how the process occur in the components. I showed a lot about the components here também. But how do we actually calculate the heat and work and power in the components? And as we expect, we will apply the first law of thermodynamics at all the components for you to calculate the power at the turbine, the heat loss at the condenser, the heat input at the heater, and the power input at the pump to make the flow to actually flow. Okay, so here we'll have the cycle, as I told you before. I know all the states at the entrance of all the components here. So here, as I told you, we will have some temperature, some pressure, and some entropy. Here at point 2, we will have also a temperature, a pressure, and a vapor quality. Here, as I told you before, also we have the entropy is the same as point 1 because this process is isoentropic. And here at point 3 we will have vapor quality 0 because we don't have any vapor, we have only saturated liquid. If you look at any thermodynamics table, for you to calculate the entropy and the specific volume, we'll have the vapor quality, and we also know that the pressure at point 3 at the outlet of the condenser is the same at the inlet of the condenser because this process occurs in the constant pressure. Here at point 4, we know that this process between 4 and 1 occur at constant pressure because pressure 4 equals pressure 1. We also know that the process here at the pump is isoentropic too. Entropy 4 is equal entropy 3. And this is one consideration that's very important for us to know how to calculate all the process, all the heats and the works and powers inside the component. The specific volume in point 4 equals the specific volumes of point 3. And that's because here at the outlets of the condenser we have saturated vapor. Okay, so the temperature of point 3 is equal saturation temperature for pressure 3. Okay, so here at point 4 we'll have also liquid. So when we increase the pressure of a liquid, the variation of the volume, it's very low. Okay, so as an approximation, we can consider that the volume at point 3 is the same as point 4. Okay, and this will be very important for us to calculate the power here at the pump, and we'll talk a little about at the next slide. Here I will show you how how we can use this entropy, this entropy equality between point 0.3 and point 0.4. So the enthalpy between point 0.4 and 4 and 3 can be used about this integral between the point 0.3 and point 0.4. And here we will use that here the function will be the specific volume plus the variation of the pressure. As I told you before, between points 3 and 4, the volume will be constant. Be it the volume at point 3, it equals the volume at point 4. So we can use as a constant and take out of the integral. So here we will have this equation. This equation shows that enthalpy between points 3 and 4 and 3 equals the volume, the specific volume of point 3, multiply for the pressure difference between point 4, or the outlets of the pump, and point 3, the entrance of the pump. Okay, so we found here a relation between the pressures and inside at the entrance and the outlets of the pump, using a consideration that the specific volume is constant between points 3 and point 4. And this equation here will be only used because these processes occur at an isentropic way. Okay. So here now we will apply the first law at all the components. Of course, here the pump already showed how a relation between enthalpy at point 4 and point 3. But now we will apply at the heater. In the heater here we won't have any work, any power occurred here at this component. We will have the only energy interaction here will be this heat here, the key heater. Okay, I told you here, I put it here in red. So if we apply the first law here, we'll have the heat input at the heater here will be the mass flow rate. Okay, the amount of mass that passes here in a certain period of time. Multiply about the difference between enthalpy at point 1 and point 4. Okay. At the turbine we'll apply the same law, the first law of thermodynamics. Here at the turbine, as I told you before, we won't have any heat input or heat outlet. The only energy interaction here will be this power produced here at the turbine. So if you apply the first law here at the turbine, we will have the power produced here at the turbine will be the mass flow rate, is the same, and it's the same of the heater, multiplied for the difference between the enthalpy at point 1 and enthalpy at point 2. Here the condenser will apply the same law here at the heater. We won't have any work or power produced here, but the energy interaction we have here, it's the heat outlet of the condenser. And here for us to calculate this heat loss at the condenser, we use the same mass flow rate here at the heater and the turbine, multiplied about the difference between the enthalpy at point 3 and enthalpy at point 2. And remember, okay, the pump will have this relation between enthalpy and the pressure difference and the specific volume here. Okay. And if you want to calculate the efficiency of this cycle, we use these relations here. The efficiency, we use this Greek letter here. It's calculated with the liquid work at the system divided by the heat input at the heater. Okay, we will use a lot of heat to produce power here at the turbine, but some of this heat we will use to move this flow here with the pump. Okay, so the pump will spend energy. Okay, and this liquid work we will say here. So we use here the power produced here at the turbine minus the power used here at the pump to produce this pressure difference and to make the flow to exist. Okay, so this liquid work will be the power produced here at the turbine minus the power used here at the pump, and the specific work here, the turbine, okay, it's calculated as I told you before, the enthalpy difference between point 1 and 2. Okay, the specific work here at the pump will be the enthalpy difference between point 4 and point 3. And as I told you before also, here we have the specific heat here, the heater here will be the enthalpy difference between point 1 and point 4. Okay, so now we are able to calculate the efficiency here at this Rankine cycle. Okay, so here in this exercise, okay, it's in Portuguese, but the link to see this exercise will be at the description of this video. It will be in Portuguese. It will be also in Portuguese, but I will put subtitles. Okay. So here we have Rankine cycles. We have the pressure here at the heater and in the condenser, and I ask you to calculate the efficiencies of this cycle. And here in this exercise 2 will be also in Portuguese, and I want you to calculate also the efficiency of this cycle. I hope my English, you understand my English here, because my Brazilian English is awful, so it's good for me to practice. Okay, please like this video and please subscribe in my channel. Okay, bye bye.